Hello and welcome to the lecture on important rock and fluid properties related to petroleum engineering. What we will be discussing today, we will cover the main important properties which are used in analyzing the petroleum reservoirs. For this, we need to first know that how the reservoir is formed and what are the properties that we need to analyze in order for predicting the performance of the reservoir, and therefore this lecture will cover that. Before starting to talk about the rock and fluid properties, we need to make sure that we are familiar with the oil reservoirs and the processes which are done before going into the reservoir and being in the direct contact with the reservoir. So for this, what we need to know is that, first of all, petroleum is actually a combination of two words, petra and oleum, which are Greek and Latin words, which is showing the oil and the rock, which is just saying that the oil inside the rock. And in order for having this, we need to have millions of years past. So with the remnants of the old creatures, dinosaurs, algae and other things, the hydrocarbons, oil and gas, are formed in a very deep levels, which are called as petroleum. Together with petroleum, there are many impurities, and we know that these impurities are water, and it can be any kind of like nickel or any other kind of gases such as carbon dioxide, so on and so forth. So the schematic for oil reservoir is something like this. This is called anticline, and generally we have within the reservoir we have gas, we have oil and water. So these gas, oil and water, these are actually within very tiny void space, and we just refer to that as porosity, and that will be one of the parameters that we will be discussing today. The oil and gas reservoirs, they are found with different approaches. It can be geological, geophysical approaches. When we say geological, it means that we will see some part of this in the surface, which is actually called as outcrop, or we can do other approaches such as seismic or magnetic survey, gravity survey. And when we have some initial sense, then we drill a well. When we drill the well, through this drilling process, we do some measurements, and one of those measurements are called well logging, which is actually giving us the values for this rock and fluid, generally rock properties. So the result of this will be the properties that we will be discussing today. So in order for having some oil and gas reservoir, of course we need to have some void space, which is actually these tiny pores here, the void space. The oils are actually, if we consider the porous media, something like this, there will be some grains here and there will be some free space. So this is called the void space, and these are called matrix or grain. The fluids are actually within this void space. So in order for having some oil and gas reservoir, we need to have some value for this void space. So we need to have a minimum value for this void space, referred to as minimum porosity. We need to have a certain amount of these hydrocarbons, referred to as saturation, and we need to have the ability for in the rock so it can transmit the fluid, which is referred to as permeability. Of course, the volume of this altogether are very much dependent on the thickness of this. So thickness, porosity, saturation, and the permeability are very important parameters that we need to have for having some economically viable reservoir rock. So as I mentioned, porosity is the ability of the rock to keep the fluid. So we will have this void space, and in order for knowing the amount of the fluids within the rock, we need to deal with a parameter which is called porosity. Saturation is actually specifying how much of this void space is occupied by some specific fluid. So when we say, for example, gas saturation, it shows the volume of the gas within that void space. When we talk about oil saturation and water saturation, similar to this, it's just showing the specific volume for some specific phase. The permeability, we said that it's the ability of the rock to transmit the fluid. So it is possible that we may have this fluid inside, but it cannot go toward the wells, the oil well. And well, in that case, it will not be possible to produce that oil. So permeability is also one of the important parameters that is needed to be dealt with. Yeah, so generally when we talk about these pore spaces and porosity, these are, as I mentioned, these are analyzed through the well logging and the measurements. So these measurements are generally together with the types of the rocks. When we talk about the types of the rocks, generally the hydrocarbons can be in the sandstones, which are mainly SiO2 based. So this can be also sealed, also conglomerate can be the type of the sandstone. We may also have carbonates. Carbonates are generally limestone and dolomite. Limestone is generally calcium carbonate. Also chalk shows kind of like similar behavior in the well logging as the limestone. So, and that's why chalk can also be considered as the carbonate. And dolomite is another type of the carbonates, which is mainly a mix of magnesium carbonate and calcium carbonate. We may also have other types, such as clay, anhydrite. Anhydrite is mainly about calcium sulfate, and also we may have gypsum together with anhydrite, which is actually similar to that in terms of the composition, but we will have additionally water crystallines. So these are actually the types of the rocks that we may have oil within this, and those are generally, those classifications are generally used together with well logging. So again, the porosity, if you want to put it in a sentence, is equivalent to the voidage, or the ability of the rock to hold the fluid. So this porosity can be any space between these grains, so which is shown here. It can be the vogs, or the vogs are actually kind of like narrower than this. Can also be considered as the part of the porosity. Generally, porosity, other than this well logging, can be measured in the core analysis, something which is called routine core analysis, RCAL, and there we just apply some conditions of pressure difference, and then we may kind of like do the measurement of the porosity in the lab. Yeah, so it is very much simplified here, but generally the oil reservoirs are very complicated. You can see here we have a metal cast showing something closer to the structure of the pores down there. So it is not this much simple, and theoretically we try to simplify that so we can do the analysis and the calculations. Porosity can be primary or secondary. So there are actually two classifications for porosity. Porosity can be classified in terms of their sedimentation, like at which part of the sedimentation they are formed. So it can be primary or secondary. Primary is happening during the sedimentation process. Secondary is generally happening after this due to some process such as dissolution or fracturing, which are generally increasing the value of the porosity, mainly also increasing the value of the permeability. Another classification of porosity can be effective or total porosity, because there can be some part of the pores which are not connected to the well, and we generally call this as isolated, and we may want to exclude that in our calculations of the porosity. Well, in that case, if we consider only the interconnected void space, then we are calculating effective porosity. The formula for porosity is actually equivalent to the pore volume, shown as Vp, and the bulk volume. So if I want to show this pore volume and bulk volume here, bulk volume will be the gross volume is actually the total volume that we have here, and the pore volume or void volume is actually the volume of the free space that we have here. So porosity is actually defined as a ratio of pore volume over the bulk volume mathematically. The values for porosity in reality can be different, but if we want to talk about the value of the porosity theoretically, we can have some models for that. So one of the models for that is to use marbles. And when we say this, it is actually like this, that we have some kind of like square. I'm showing this in 2D only. And we may have marbles of equal size. So this can be like this. Please neglect these ones. So we have a bulk volume, and we have 4 marbles. And this is actually 3-dimensional, which is just showing that we have 8 marbles within a square. The side can be anything like A. The volumes of the marbles should be equal. And this kind of like packing is called a cubic packing, which is giving us the value of the porosity equivalent to 47.6%. In reality, the porosity can change in the values between 3% to 40%. So this is kind of like very idealistic approach for the value of the porosity, because in reality we have different size of the grains, and also the packing may not be like this, and there can be some kind of like angles. As you can see here in the second figure down there, there can be some other angle than this 90-degree here, and that will create another types of packing. So this is called a cubic packing, but we may have rhombohedral or orthorhombic or different types of packings, which is kind of like compressing this, ending up to the less values of the porosity. So the value of the porosity that you see as 25.9% is actually the value of the porosity when you have the packing for the rhombohedral. You can see the value of the porosity for different types of the rocks that we mentioned. Yeah, so the saturation, we said that porosity generally show the void space that we have here, but it is not actually specifying how this void space is filled. And for doing that, generally we use another parameter, which is called saturation. Saturation is specifying how this void space is filled with which type of the fluid. And that's why if we want to mathematically show the saturation, it will be, if we want to show the saturation for phase alpha, it will be the volume of that specific phase over the pore volume. Now, if you remember, the porosity had the formula of pore volume over bulk volume. So you see it is kind of like specifying the pore out of this bulk, and the saturation is kind of like showing specific volume over the pore volume. So it can be the saturation for oil, it can be saturation for gas and water. Generally, saturation for water it has some minimum, which is called the irreducible water saturation, because when at the time of the formation of this reservoir, the oil is migrated from the source rock to the reservoir rock, and initially there is water there. And since oil cannot displace all of this water, there will be some minimum value for this water. And that's why there is always a minimum value for water saturation as connate water saturation. Yeah, so as you can see here, we may have some oil reservoir which has only oil and water. Well, in that case, since this is kind of like percentage, they generally need to sum up to 100% or 1. So if we have oil reservoir, we just say that the saturation of oil and water should be 1. If we have gas, then the saturation of the gas, oil, and water should sum up to 1 or 100%. This is an example that gives us the values for bulk volume and grain volume, and it asks for the calculation of the porosity. So if you follow this formula, so we see that the givens are bulk volume and grain volume. From here, we can know that the bulk volume is actually equivalent to the sum of grain volume plus the pore volume, right? So we have bulk volume and gross volume, and it contains only grain and pore. So some of them should be equal to this. So we can just write this equation in this form as well, that pore volume can be equal to the difference of the bulk volume and the grain volume. So if we just replace V pore by bulk volume and the grain volume, then we can solve this problem. So as you can see here, we just write the formula in this form, and then we replace the given values, and you see that the result will be 17%. Another problem is also given. So we said that the porosity can also be measured in the core analysis, which we just call it as routine core analysis or RCAL. So there is some analysis done on a core taken from a reservoir. It has a bulk volume of 86 cubic centimeter, and we know that the volume for gas is 5 cubic centimeter. We have the oil volume and we have the water volume. So as a first part of this problem, we need to find the value for the porosity. So we know that the porosity has this formula, and we know that pore volume is actually sum of the volumes. So we can just write it in this form, that the pore volume is equivalent to the sum of the volumes of the fluids there. All these volumes are given, so we can find the pore volume easily. And then we just replace it into this formula, and the bulk volume is given, and we can find the value for the porosity. For finding the saturation, we have the pore volume and we have the volume for each phase, each fluid. And if we divide the volume of each phase to the pore volume, we will get the value for the saturation. So as you can see here, first the total pore volume is calculated by summing up the volumes of the fluids, and then the porosity is calculated with this formula, and then we can find the values for the saturation of each phase. As you can see here, some of the saturation values are equal to 1. So we said that in order for having economically viable reservoir, we need to have also a minimum value for a permeability. When we say permeability, we define permeability as the ability of the rock to transmit the fluid. Because if we have the fluid down there, if we have the well, But in case that there is no flow of this, well, in that case, it will not be kind of like economically viable for us to produce that. And that's why permeability is very important. And it is measured during the drilling process through a test which is called drill stem test. Also, it can be analyzed later and also through a process which is called well testing. Generally, for the definition of the permeability, we use some equation found by a person called Darcy. So we have Darcy's equation. Darcy was a hydraulic engineer, and he found this by some experiment of through some pack of sand, and he just applied some pressure difference, and then he just found out that the rate is proportional to some parameters and inversely proportional to other parameters. And based on that, he just defined a parameter called as permeability. So you can see here that Darcy is defined. I just write the Darcy equation here in this form. So we can use this equation for the definition of it. So 1 Darcy, so this is the permeability. So 1 Darcy, if we have a rock with 1 Darcy permeability, we will have a flow of 1 cubic centimeter. If we have a fluid with the property of 1 centipoise viscosity, and if we apply the pressure gradient of 1 atmosphere per centimeter, and if the cross-sectional area is 1 square centimeter, then the permeability is 1 Darcy. So for that, we used this equation to define the 1 Darcy. So you can see here the equation. Here, this Q is flow rate. The mu is viscosity. It is showing the resistance to flow. So consider that we have, I will just give example from some 2 fluids that everybody knows. So if we have honey and water, we know that honey will flow harder than water. And well, in this case, we just say that the viscosity of honey is higher than water. So that parameter is used in petroleum industry. And we just have the viscosity of oil here. A is the cross-sectional area. So if we have some kind of like pathway like this, the cross-sectional area will be the area perpendicular to the flow. So the flow is happening from this pressure to the like P1 to P2. The flow is in this direction. This will be L. And this will give us the cross-sectional area, A. So we need all of these things. So we can just put that in the equation and then get the value of our unknown. Yeah, so here you can see that Darcy found out that when we have the flow, generally the rate is directly proportional to the cross-sectional area. So if we have like wider cross-sectional or bigger cross-sectional area, the flow is higher. Also, it's directly proportional to the pressure gradient and inversely proportional to the viscosity. And he just put them all together in one equation. And then he just changed the proportionality sign to the equal sign by adding a coefficient, and that coefficient is called permeability. So here we said that in the Darcy's equation, the units for this, so this is a cubic centimeter per second. This is centipoise. This is square centimeter. And this is atmosphere and centimeter. And we will have here the Darcy. So these are the units. But in reality, Darcy is very big value. So in the oil reservoirs, we generally don't have that high permeability. And that's why instead of this Darcy, we may want to use millidarcy. I want to add here that centipoise is equivalent to millipascal second. For knowing more about viscosity, you can go and read about Newton's law for fluids, and this millipascal second, the unit for this is coming from that formula. So the value for this permeability, as mentioned, generally are less than 1 Darcy, and that's why we tend to use millidarcy rather than this Darcy. There are some cases that the permeability value can be higher, and that is generally happening for the case that we have fractures. If we have that, well, in that case, yeah, we may have the permeability value of like 10 Darcy. But if we talk about conventional oil reservoirs, generally the permeability is not that high, and that's why in the equation we use millidarcy, and then we use a conversion factor here. Permeability is having different values in different directions. So if I want to give example, so everybody knows about velocity, that velocity can be different in different directions. So, and generally we define the directions as X, Y, and Z. Permeability has the same thing, and permeability can be different in different directions. So we may have this permeability in X, in Y, and Z directions. And if the values in different directions are the same, well, in that case, we just say that we have isotropic permeability. But if it's different, which is actually the case in reality, well, in that case, we just call it as anisotropic. This Darcy equation, it has some assumptions. So the equation is not valid actually for all cases, and there are some assumptions here. And if the assumptions are valid, then you can use this. The assumptions are the flow should be laminar. Generally, laminar is defined based on a parameter which is called Reynolds number. So when we have flow, the flow can be laminar or it can be turbulent. And this classification is done based on a parameter which is called Reynolds number. For using Darcy equation, the assumption is that the flow is laminar, which is equivalent to having a Reynolds number less than 2000 or 2300. If you don't have that, and if you have turbulent, then you cannot use Darcy equation in this form, and there should be some kind of like modifications to this, which is out of the scope of this lecture today. Another is that the flow should be steady, which means that there shouldn't be any time change. There is also another assumption that the saturation should be a single phase. Which means that the saturation for that specific phase should be 100%, and we cannot have more than one fluid in this form. If we have more than one fluid, then we need to modify this the same way that we did that we need to do for the turbulent. There shouldn't be any reaction between rock and the fluid, and the rock must be homogeneous. So here we just when we talk about this permeability, we said that the reservoir should can be isotropic or anisotropic, which is actually related to the values of this parameter in different direction. There is also another thing which is defined based on homogeneity, homogeneous or heterogeneous, which is coming from the values at different points of the reservoirs, not different direction, but different points. For using Darcy equation, we need to have homogeneous reservoir as well. So this equation in this form is written in Darcy's unit, and there are in different countries they are using different units for different parameters. For example, For pressure in Azerbaijan, they may use like bar or atmosphere, but in UK or US, they may use PSI. That's why in that case, we need to just add some conversion factor here, so we can use the values without any conversion. Because when the value for the pressure or any parameter is given, so you have two options. Either you need to change the unit for each parameter each time, or you can just have a general formula with conversion factor, and then you can use the values directly in that. If we want to use the values directly in the equation in some unit system, which is called field unit, very much similar to BTU. Well, in that case, we need to add a conversion factor here, and that conversion factor is equivalent, as you can see here, is equivalent to 1.127. And depending on using permeability in Darcy or millidarcy, you may have also this multiplication by 1,000th in the conversion factor. This is another example. If you remember, we said that porosity can be measured with some test, which is called routine core analysis. We may also do the same thing for permeability, and if we do that, then we need to use this equation, Darcy equation, so we can find the value for the permeability. So I will not talk about the details of that, but the problem that you can see here are very much similar to the process that we need to actually have for calculation of the permeability while doing the measurement using the core. So what we have here is that the properties of the fluid is given. So the viscosity of the liquid is given. We have the length and the cross-sectional area that can be found from the core radius, and then we have this pressure differential. So you can see here all the values are given. We have the rate. As you can see there, fluid flow is this part of the equation, and if we just put them in the equation, then we can find the value for the permeability. So as you can see here, they just sort out the equation based on permeability, and then they just replace the values and found the value for the permeability. What we've discussed so far, porosity, permeability, these are related to rock properties. Saturation is related to both rock properties and fluid properties. But if we want to talk about important properties related to fluid, we may want to discuss the density of them. So density measurement can be done in the surface condition, which has the condition of 14.7 psi and 60 degree Fahrenheit, or we may have this in the reservoir. So if we talk about the surface condition, well, in that case, there is a parameter which is called specific gravity, and this is actually the ratio of the density of the fluid to a reference density. Depending on the type of the phase, we may have this reference differently. So if it's gas, the reference will be air, and if it's liquid, the reference will be water at these conditions. So for the case of gas, we may write this specific gravity. Again, this specific gravity is defined for the surface condition. It is shown with gamma, and gamma for gas is equal to the density of the gas over the density of the air at this standard condition, pressure and temperature. From ideal gas law, you know that we can write the ideal gas law in this form, that P molecular weight is equal to rho RT, and therefore we can just write rho as P molecular weight over RT. And we can replace it there So this will be actually equal, so we can get rid of the pressure and temperature. These are the same. We said these are surface condition, and R is constant. It's universal gas constant. So we can write this specific gravity as a ratio of molecular weight of the gas to the molecular weight of the air. Molecular weight of the air is equal to 28.97. So for the case of gas, we may write the specific gravity as a ratio of the molecular weight over 28.97, or you can just write it as 29. We have for the case of liquid, this will be the ratio of the liquid density to the reference, which is actually water. So it will be the density of water. And this, unfortunately, we don't have any kind of like formula like this. So it will be in this form. The thing here, important thing about the liquid specific gravity is that this is used in finding a value which is called degree API. So when we talk about oil and oil quality, this quality is defined based on different kind of like criteria. So one of the parameters important there is degree API, which has a formula based on this specific gravity. This degree API is equal to specific gravity. So with finding this, we can get the value of the degree API and then talk about the quality of the oil. And this is one of the important applications of liquid specific gravity, as you can see there. Okay, so there are also some other parameters related to rock and fluid, but I will not discuss the other parameters here in this lecture, and I will move to the drive mechanism. So when we say drive mechanism, it is closely related to the production of this. So oil production So this is referred to, when we want to produce, we just refer as drive mechanism. So when we want to produce oil, we may have natural drive mechanism, so we don't actually inject anything or use any kind of like artificial thing for producing. Or we may just use the energy of the reservoir down there, and we can just produce the oil naturally. And this drive mechanism, what we will be talking about today about drive mechanism, are three types of natural drive mechanism. These are classified as solution gas drive. We may have gas cap drive, and then we may have water drive. The general idea here is that we just use the energy of the reservoir in these forms so we can produce oil. In the solution gas drive, what happens is that, if we have the oil reservoir, so this is oil. Depending on the value of the pressure that we have here, and the value, if we have reached to the bubble point pressure or not, we may have this gas cap or not. For the case of solution gas, we don't have that gas cap, which means that the pressure is above bubble point pressure. When the pressure is above bubble point pressure, we just call the reservoir as undersaturated reservoir. So for the case of undersaturated reservoir, when we drill this well and when we just do this perforation, creating connection between well and the reservoir, at the time of the production, there are this gas dissolved in the oil. So when we have that, this dissolved gas can go in different direction. Either it can go toward the well, or it can go upward to create a secondary gas cap. So depending on the properties of the rock, mainly related to permeability. So if we have permeability in this direction higher, so the gas bubbles will just move upward, and if we have permeability better in this direction, it will just move toward this. So in the solution gas drive, what happens is that the oil will just be moved toward the well, and the gas bubbles together with this will just move toward the well. And when they move, because they're moving like faster and easier than oil, together with itself, it will just move some oil as well, ending up to higher oil production. For the case of gas cap, what happens here is that pressure is lower than the bubble point pressure, and here we have a gas part. And when we have this, so what happens together with the production, the gas starts to expand. And when they expand, they will just push this downward, pushing the oil toward the perforation, and it will cause like additional recovery. For the case of water, it is very much similar to the gas cap, but we know that based on the density, water is below oil. And when we have this water down there, it is also referred to as aquifer. It will just push the oil upward, causing like additional recovery. So these are kind of like the overview of the drive mechanism that we have. Of course, there are analysis of this that in order for doing the analysis, we may want to see how the pressure is changed, how the rate is changed, how the gas production is affected. Based on that, we can just discuss the effectiveness of each recovery process. So what you see here in the solution gas drive, so these are the profiles that I mentioned, but we will not discuss it here today. And what we see here is that recovery factor. So recovery factor is something very much similar to efficiency. So it's the part which is produced. So down there we have some volume of hydrocarbon, and some part of it will be produced. This ratio is called recovery factor. You see that for the case of solution gas drive, recovery factor is somewhere between 5 to 30%. As for gas cap drive, so you see we also have profiles for analyzing this. The recovery factor for this will be a value higher than the solution gas drive. They're forcing from this. We expect high recovery, of course, in the gas cap drive, and you can see that it's some value between 20 to 40%. Water drive shows better support. It is actually very much close to a process we just call it pressure maintenance. So this water will just help us to maintain the pressure, because when you produce the oil, pressure is decreasing, and water will just come and replace the voidage here due to oil production, and it will just maintain the pressure. And as I mentioned, this aquifer influx or water encroachment is used for supporting the recovery process. So finally, what I want to discuss, here what you see here, this water drive can be related to two things. This water can be kind of like connected to the surface. Well, in that case, we just call this aquifer as like artesian, or it may not be connected to this to the surface. Well, in that case, we just call it as like confined aquifer system. Finally, I want to show you different types of reservoir. So generally, reservoirs are classified as like gas and oil reservoir. For the case of gas reservoirs, we have dry gas, wet gas, and we have condensate or retrograde condensate. And for the case of oil, we have volatile oil and black oil. So why I mentioned this, because we discussed that the properties should be measured or calculated. So here is one of the applications of that. So we need these properties so we can do this classification. As you can see here, there are different parameters there as like GOR, gas-oil ratio, degree API we mentioned. So you see that degree API is used for this classification, this gas-specific gravity, and very much importantly, we use the composition of the fluid down there. So this was a lecture for today. I tried to cover the main rock and fluid properties, and also I wanted to give you a general idea about drive mechanism. Hope it was helpful, and thank you very much.